Greetings, ladies and gentlemen. Let me give you an overview of optimization of high throughput virtual screening process and give you a demonstration on the project. The roadmap for today is this, and let me give you a brief introduction about what is virtual screening. Virtual screening, at the face of it, is actually reducing a very large database into a database of a tangible amount. So where is this applied? Virtual screening is a sub-process in drug design. Normally, when a receptor is identified as the cause of a disease, one needs to find small molecules of the same structure as this receptor so that the small molecules would bind to the receptor and slow down its metabolic process. Once you identify these small molecules, you have to experiment with them in the laboratory level and optimize them further in order to make a drug. That is why you have to reduce the 10 into power 13 plus ligands into a tangible amount of ligands with which you can experiment at the laboratory level. Essentially, virtual screening is a repeated application of molecular docking. Molecular docking is similar to the lock and key problem, in that we have to identify the correct orientation of the key that can be used to unlock the lock. We can think of the orientation as the key size, which direction the key should be turned, etc. In our context, the receptor can be thought as the lock, while the ligands are the keys. Molecular docking is an optimization problem where we have to identify the best fit orientation of the ligand that would bind to a certain receptor. These were the objectives for our project. We wanted to develop an open source high throughput virtual screening environment to carry out drug designing process here in Sri Lanka. And we wanted to reduce the overall time for drug designing process using multi-core processors with parallel computing and soft computing methods. And we also wanted to contribute to identify drug targets for HIV/AIDS. This is the flow of our first phase, and this is the architecture we used. As you can see, we have created an abstract layer that would take care of job scheduling, and we have introduced data level parallelism to a very prominent docking software called Autodocvina. Autodocvina already had instruction level parallelism, but with the results you can see that we were actually able to introduce a very significant level of throughput enhancement. This is the rudimentary results of our experiments, and we actually summed up the results and tabulated it for the purpose of convenience. As you can see, we have introduced more than 600% throughput enhancement, or 6 times throughput enhancement that of the nominal or the conventional process, which is really significant. Think of it in this way. Imagine you have a relative who has an unknown disease which doesn't have a developed drug as of yet. This is the difference between him suffering for 6 years and him getting over the disease by a novel drug developed using this method within 1 year. So that is a significant achievement. To add to that, Dr. Oleg Trot from Fight AIDS at Home has acknowledged our enhancement, and he has also agreed to deploy our code base into the worldwide effort they have put through to identify AIDS drug targets. IBM crew is going through our code base as of now, and they will integrate it with the worldwide network within the next year. This is the conclusion for the first phase. As you can see, data level parallelism can achieve better speed enhancement, and we can clearly make better use of multi-core environments with our implementation. To signify that this is a novel process, this research paper was published in ICIFS 2012 in Beijing.